the last episode.
All right, so let's put a pin on our discussion of great movies and television shows and get back to something better, which is the wonderful world of structural analysis.
Let's go.
Okay. All right, so I have to ask, did I gain your trust back when I said that homework 2.3 was easier than homework 2.2?
Yeah, a little bit. Just a bit.
I got a lukewarm yes. Okay. So
Still thinking about it.
I'll say this, there's only one problem on this assignment. It's a little bit longer, but I'm going to try and give you some hints to make it more doable. Today what we're going to do is we're going to close out our topic for support reactions, which is it's sort of a nice day to close out a topic because we're not going to be here on Monday because we have the holiday coming up. So when we come back from the holiday, we'll be in the land of trusses. So this will be our last day to discuss reactions, and so we're going to deal with internal hinges today. That's something we haven't talked about, and it'll be we have to use a new analytical tool to be able to solve those problems. I'm still working on grading homework 2.2, and I know you submitted homework 2.3 today. And so what I think I'm going to do is, between now and Wednesday, just sort of try and chip away at all of the outstanding structural analysis homework so that when you come back, it's all sort of graded and taken care of. I did go ahead and grade for the vast majority of you that are in 321. I graded the first homework in there, so that one's done. So I'll just take this one, basically take this class all in one big chunk. Okay, so I am giving you a homework today. It's due Wednesday. Obviously, it's not due Monday. So yeah. Sound good? All right, everybody gets code. Okay. All right. So today we're going to talk about internal hinges. Okay, and it's really the last thing left to discuss is the process of dealing with an internal hinge or an internal release. We will deal with more types of internal releases later when we discuss the theory of influence lines, but for now, and for the vast majority of the semester, the internal hinge is the most ubiquitous release that we'll deal with, so that's what we're going to focus on today. So let's just make sure we know what we've talked about so far, and to be honest, we've talked about pretty much every analytical component that we're going to deal with, not only throughout this semester, but really like as a structural engineer. I mean, being able to handle concentrated loads, distributed loads, concentrated moments, and these three boundary conditions will get you through 95% of every single structural engineering problem that you'll deal with, because they pretty much all are comprised of these components. So that's why I sort of structure the class this way, because this is what we do. We do this day in, day out. Okay. Now, the one thing we haven't discussed from a reaction standpoint is how to compute reactions for internal releases. So again, we did talk about internal releases last week when we discussed stability and determinacy, when we were classifying structures with whether or not they were unstable, determinate, indeterminate. We said that internal releases were present. Well, today we're going to dig into that a little bit more. Okay, so the symbol that I'll use is I'll probably just draw like a little circle in the beam. That'll be indicative of an internal hinge. And we've talked about a couple real-world examples. Namely, you'll find that you can assume something to be a hinge. For example, if you're talking about steel design, you can assume something to be a hinge when it transfers shear, but it doesn't transfer moment. Okay? So a good example of that would be a connection like this, where the webs are connected, but not the flanges. Same thing here in this pen and hanger connection. At the end of the day, if the connection is designed to transmit shear and not transmit bending, you can treat it as a hinge. Okay? Now, the way that we deal with an internal hinge is we break out the secret weapon of structural engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan, and you break out the idea of cutting a section. Now, we talked about this a little bit on the first week, but just to explain what I'm talking about here is, first off, I'm using this idea of cutting a section as a specific tool today to deal with internal hinges. But I don't want to skirt this by saying that cutting sections are only used for this. The idea of cutting a section and the process of cutting a section is an incredibly powerful tool for an analyst to ascertain structural response. Okay? The idea is, for example, if I have a table here and I'm sitting on the table and you break out the samurai sword or lightsaber and you cut through the other end of the table, I'm falling down to the ground. I'm gonna get hurt. Okay? And the reason is, by cutting a section, you have released the structure's ability to resist that response at the place where you made the cut. Okay? So the idea is that you can then apply equations of equilibrium to not just the structure as a whole, but the structure once it's been cut in two, and look at either component of the structure and say, what are the internal forces required at that point where you broke out the samurai sword or lightsaber in order to keep the structure in equilibrium. And those forces are what was inside the table keeping me upright and keeping me not falling down. Does that make sense? And understanding those forces, not just the forces on the outside of the structure that keeps the structure in equilibrium, but the forces inside the structure, what the structure has to be able to resist to keep the structure stable, it is those forces that we need to be able to design for, okay? And so I would argue that as structural engineers, we care about reactions, but really it's that internal response that we really care about, because it's that internal response that we will use to size beams, size columns, etc. So the idea of cutting a section can also be used to validate some answers, determine equations for shears and moments, which will be important later when we compute deflections, etc. Okay? So to go through a little bit of an academic breakdown of this, okay, let's talk about this. So what happens when you cut a section? So I have a beam, I take a samurai sword or lightsaber, and I cut through the beam, and I get some response, okay? So let's talk about these responses, and let's see if we can talk about the, this one's done. Let's talk about the responses on each side. So maybe what I'll do is I'll break this information down that's on the slide here a little bit, okay? So what I've done here is I've taken this samurai sword or lightsaber, and I've taken the ends and I've spread them apart, okay? Now I propose, okay, if we look at, let's say, come on. Hold on, I think this is frozen. Uh-oh, hold on. Uh-oh, it's frozen. We're going to restart PowerPoint on the fly. Come on. Let's try this again. Am I still recording? Yeah, I'm still recording.
Are you going to edit this part out?
Nah, we'll leave it in. There we go. Okay. We're back. Okay. All right. So what I'm going to do is, like I said, I've cut a section. Let's spread that apart. Okay? Okay. So what I want you to do is recognize that those two pieces of the beam, I'm sort of treating those as two separate structures. They're two completely different structures. Okay? And I propose that when you cut a point through an arbitrary section, I propose you have at most three unknowns. Okay? So let's just break down those one at a time. So first off, let's talk about forces in the x direction. Is there a possible unknown force in the x direction? Yes. Okay? Now what I might do is this way, I might say there's an unknown force acting to the right. Okay? But I propose that because of Newton's third law, that if I look at the other side, it's got to be acting to the left. Okay? that on the other side of the section, it's an equal and opposite response, okay? Here's, like, if you're wondering why they're drawn in opposite directions, let's just be clear what we're talking about. We're talking about the internal response, okay? Here's a pencil. I'm going to take the pencil and I'm going to apply tension, okay? So in other words, if I want to apply tension, I want to take the pencil and I want to make it longer. How do I do that? If I have this hand here and I have this hand here, I take my hands and I pull them in opposite directions. One hand goes this way, one hand goes this way. My hands are doing the same thing to the pencil. I'm taking the pencil and I'm yanking on it. I'm stretching it. But in order to apply that stretching effect, one force has to go one way, one force has to go another way, okay? And so for static structures, they're always going to be equal and opposite, okay? So for example, the vertical force, if the vertical force unknown is, let's say, down on this side, it's going to have to be up on this side, okay? What am I doing there? I'm shearing the section. I'm taking it, I'm shearing it. So how would I take this and shear it? I have to take one hand and go up, one hand and go down, equal and opposite. Does that make sense? What about bending it? One hand has to rotate this way, one hand has to rotate this way, right? So the moments are going to be equal and opposite. So maybe one moment goes like that, one moment goes like that, okay? Does that make sense? Those are the internal responses. Now what I'm getting at is it doesn't really matter whether I investigate the left side of the structure or the right side of the structure. Whatever value I get for P over here, I'm going to get the same value here. Whatever value I get for M here, it's going to be the same here, just in an opposite direction. Okay? Does that make sense? Okay. That stuff that I'm talking about right now, this is going to be incredibly important later when we discuss shears and moments. For now, because we're dealing with reactions and we're dealing with internal hinges, the funny thing is we actually don't care what the values of these are, and here's why, okay? We care about what the values are when we're interested in those values at that point. For these problems, we're not interested in that. We're interested in support reactions. So why cut the hinge, okay? Here's the reason. When you cut a structure or a section through an arbitrary point in a structure, you get 1, 2, 3 unknowns. 1, 2, 3 unknowns. Now again, it's possible some of those unknowns are 0, like they are with reactions, but at the end of the day, they are unknowns in a general fashion. Bless you. Now, why do I have 3 unknowns here, but only 2 unknowns here? Because I'm cutting a section through a hinge. When you cut a section through a hinge, notice how I have a force in the x direction, I have a force in the y direction, but I don't have a moment. Why are there moments here, but not here? Because if you cut a section through a hinge, you already know what the internal moments are at a hinge. And the internal moments are 0. There are no moments at a hinge. That's what a hinge is. A hinge is a moment release. The structure cannot resist internal moments at a hinge because a hinge doesn't resist moments, okay? So what we are doing is using the fact that we know what the internal moments are right here to address our problem, okay? So, okay. All right, one thing I'll mention about the slide I just had and the diagrams that I drew. So I broke this up into 3 separate images. You'll notice here that the sign convention I've got here, so I'm saying that this is positive axial forces, this is positive shear forces, this is positive bending moments. That is the traditional sign convention we use in civil engineering structural analysis. I'll be frank, it's not really going to matter today, but it is going to matter a whole lot when we draw shear and moment diagrams. You probably remember this from statics, but we utilize a graphical approach to construct shear and moment diagrams, and that graphical approach assumes that this is our sign convention. So we do need to respect it in order for that graphical approach to work. And as for positive axial forces, these forces are indicative of tension because here's a section cut, the force is pulling away. Here's a section cut, the force is pulling away. Forces that pull away increase length. That's tension, okay? So we basically say that positive axial forces are in tension, and there's positive shear and positive moment. Later on, this will sort of be like a memorization thing, but for now, I'm just throwing it out there as food for thought, okay? What I want to do for the rest of lecture today is see if we can utilize this internal hinge to solve this problem, okay? Now, Does anybody see, before we do any math, does anybody see a problem that we might be having or a challenge that we might be having with this structure? There's 4 unknowns. Interesting. There's not 3, there's 4. We have 1 more unknown than we're used to dealing with. That's tricky, isn't it? Okay. Now, is this structure determinate? What is the stability and determinacy classification of this structure? Is this structure stable? I mean, the reactions are not all concurrent. They're not all parallel, right? I mean, let's identify those reactions. What do we have? We have 1, 2, 3, hold on, and 4. So we'll call that AX, AY, BY, CY. So we've got 4 unknowns, 4 reactions. Do we have any equations of condition, some E sub C values? Looks to me like we've got one right there, right? Because we've got a hinge right here. So 4 minus 3 plus 1 is 0. The reactions are not all concurrent. The reactions are not all parallel. This structure is stable and statically determinate. There is no reason that we cannot compute support reactions using simply the principles of statics. But without a discussion about hinges, this problem would be a little bit on the challenging side, hence why we're talking about it. Okay. Now, for now, what I'm going to do is I'm going to ignore all this hinge stuff, and I'm just going to try and do the problem the way I've been doing problems this whole time, okay? And let's just see what happens when we do the problem the way that we've been doing it. Okay, so let's start off with these distributed loads. So each of these are 15-foot spans. So I can take this first distributed load and idealize that as 30 kips. And what's this distance right here?
7.5 feet.
There's 7.5 feet. Okay, this one over here, I'll do this one over here on the right. 1.2 kips per foot over a distance of 15 feet is going to be what? 18? Did I get that right? Did I get that right, actually? I think yeah. Okay. And then this triangular load, that's going to be 4 times 15 over 2. So I'm going to collapse that as a 30-point load, or 30 kip load. Okay. All right. So there's that. Okay. So first off, anybody see a reaction that's really easy to figure out?
Sum of the forces in the x direction.
There we go. So if we sum forces in the x direction, we know that AX is 0. So good, we've got one. That one's pretty straightforward. Okay. So there's that. Now, okay. I'm already feeling a little uneasy because I imagine, this is not like the normal problems that we've done. We've got too many unknowns, but let's just do what we've been doing, okay? So I don't know, maybe what we'll do is we'll sum moments a day. Let's sum moments a day and let's see what we get, okay? So we'll sum moments a day. All right, sum moments a day. So do we have to consider AX or AY? No. All right, so how many forces are going down? 1, 2, 3, 4. They're all generating moment this way, right? So we've got 30 times 7.5. We've got 14 feet, or 14 kips times 15 feet. We've got this 30 kip load right here. Now, what is that? Let's see. So that's
35 feet.
15, 30, 35 feet. And then we've got 18 kips times 15, 30, 45. What is that? 52 and a half? Wait. Okay. So, now that's going to be resisted by what? Do I have to consider the AX or the AY? I'm going to have BY times what?
30 feet.
Do I have to consider CY too? And CY times
60.
60. Okay. So BY times 30 feet, CY times 60 feet. Okay. So we're going to have 30 times 7.5 plus 14 times 15 plus 30 times 35 plus 18 times 52.5. What does that come out to be?
We'll need a minute.
What's that?
So we'll need a minute.
You're going to need a minute? Okay. Wait, what?
Said on the best.
I got a different answer. That's what I got. I got 2430. Hold on. Let me check, make sure I don't have a. Okay. Okay, 2430. Is that what you said? Okay. Okay. So, that doesn't isolate a reaction. That just tells us how to compare two of them. It says that plus this times this plus that times that equals this. And one thing that you could do is you could eliminate the feet units from all this, because you could say 2430 kips equals BY times 30 plus CY times 60 instead of, because there's feet everywhere. But that doesn't really matter all that much. What I'm going to do is I'm going to do that, and I'm going to call this equation 1, okay? Because, I mean, inside that red box is a true statement. It may not be one that helps me get a value like this one did. I mean, AX equals 0. That's an answer, right? That's a variable equals this number, okay? This one is not that, but inside this box is a true statement. So we can use this for maybe a little bit later. Okay. Now, do I have what's my other equation of equilibrium? I've used that. I've used this. What's my third one? There we go. So let's sum forces in the y direction. All right. So what do we have going up? We've got AY, BY, and CY. What do I have going down? I've got 30, 14, 30, 18. Okay. So let's see, 14 and 18 gives me 32. So is that 92? Yep. Did you get that right? Okay, so this tells me that AY, let me scooch that up a little bit. AY plus BY plus CY is 92 kips. And that's a second equation. But again, it doesn't give me an answer, right? It's a true fact that I can use later, okay? So I'm not really there. I'm not there at the answer. But the reason I'm not there is because I have not utilized all of my known factors, right, or known equations. Remember how determinacy is a comparison of unknowns to knowns? Remember that? And if it's determinate, you have the same number, right? How many unknowns do we have in this problem? 1, 2, 3, 4. Which means I got to have 4 knowns. 1, 2, 3. I'm missing one. What's the missing one? The hinge. Okay? That's the issue. Okay? So what I'm going to do is break out my secret weapon. I'm going to break out the secret weapon of structural engineering. We're going to samurai sword here. Something like that. And so what I'm going to do is, the way I like to label these is I call it like section 1-1. So it's sort of like a CAD drawing. Remember how you would cut a cross section through a part and there'd be like a section 1-1 or section 2-2. And remember, like on CAD drawings, you might have you have the section cut and have the arrows, whether you look one way or look the other. Y'all remember that? Let me ask you this, okay? Now we're going to get into strategy land. Okay, I propose, okay, let's have a thought experiment. I'm sitting on the table, I'm sitting right here, he takes out the samurai sword or lightsaber, cuts to the table, I fall down, okay? What we are trying to do is recognize that we're cutting the section right here. It really doesn't matter whether we investigate this side of the table or investigate this side of the table. The response inside here will be the same, okay? Doesn't matter, right? Now, that being said, that doesn't mean we need to make our job harder, okay? So let me ask you a question. If you were to, imagine this structure was printed on a sheet of paper, and you took a pair of scissors and you cut a line right there. Which side of the structure do you think would be easier to deal with? The stuff on the left, the stuff on the right? The right. There's just less stuff over on the right, okay? So what I'm going to do is cut a section, look to the right. Okay, so let's do that. Okay, cut a section at the hinge and look to the right. All right, so what that means, what I'm going to do is imagine that I took the eraser, imagine I took this eraser and I erased all of this. What I'm going to do is redraw everything over here, and that's all I'm going to look at from here over, okay? So what does that look like? Well, it looks like this. I have a beam that looks like that, beam that looks like that. I have a roller support right here. I have a reaction here. Have I figured out what this reaction is yet? No. So we'll just call it CY. Okay? Now I have a distributed load. Like that, and it is 1.2 kips per foot. Okay, you can see here's like the hinge right there, and that's where I samurai sword or lightsaber right here. So what I'll do is I'll draw a big I'll do that. That's where I samurai sworded. Okay. All right. This is a span come on. Of 15 foot. And this is our free body diagram for everything to the right of the hinge. Does that make sense? Okay. Now I do want you to get into the practice of whenever you cut sections to ignore the point load right here, because I want you to start thinking that whenever you cut a section, you need to figure this out again. Now, in the case of this problem, it is, in fact, 18 kips right here, 7.5 feet away. Okay? Not disputing that. But that's just because we happen to cut the section right at the edge of the load. What if we cut a section through the load? This wouldn't be 18 kips anymore. It would be less than 18 kips. Okay? So I do want you to get into the habit of thinking, okay, if I cut a section through a load, I need to redo this part all over again. Okay? Does that make sense? All right. Now, there are unknown forces there at the hinge. Okay? We're cutting a section through the structure. So there's a possible force in the y direction. We'll just call it Fy. And there's a possible Fx. So now what I want you to do is I want you to think of this structure as a structure by itself. How many unknowns are there? 3. Do we really care about these unknowns right now? Well, what are we doing in this problem? We're trying to compute the support reactions, right? So I want to be clear. Are these support reactions? No. These are inside the structure. This is the ground. This is what I care about. So how do I determine the reaction at C? Some moments at the hinge. So what we'll do is we will sum moments at the hinge. Equals 0. And just so you're aware of what I'm writing, I'm saying we're summing moments at the hinge. And why do I have this arrow here? Because we're looking to the right. Okay. So we're summing moments at the hinge, looking to the right equals 0. And so what do we got? We've got so what do we have? We have 18 times 7.5 must be counterbalanced by something times 15. So that's 18 times 7.5, that's 70 and 135. Right? So therefore, was that 9?
Yep.
Okay. So we've got one of our reactions, right? That's what the hinge did for us. The hinge afforded us the ability to solve for one of those unknowns. Now I'm asking you, tell me what to do. Now what do I do?
Plug Cy back into the first equation.
There you go. And then what'll that give us?
Vy.
And then what do we do with that?
Plug it into the second equation.
because then we'll know by and cy and we get ay. So we're still going to use these equations, we just had to do the section cut first. Okay, so what we'll say is ahead of myself. Back to equation 1. Okay, so equation 1 was by times 30 plus cy times 60 is 2430. Nine times 6 is 54, so that's 540. Oh. Okay, so 2430 minus 540. Might need some help. What's that?
1890.
What'd you get for that?
For BY.
Yep.
63 kips going up.
Okay. So then what we need to do is go back now to equation 2. And adding those up was 92 kips. Okay, so we know that AY plus, in this case, 63 plus 9 kips is 92 kips, which is AY plus 72 kips. I think I can do that one in my head. And there we go. Make sense? So therefore, what's our answer? Like, what are the 4 answers? Because remember, this is a reactions problem, so we should have an answer for every unknown. AX is 0. AY is 20 kips upward. BY is 63 kips upward. CY is 9 kips upward. Okay. All right. Let's take a step back, because I'm going to give you some hints on your homework assignment before we leave. So, what?
It means we need hints.
No, I really don't think you do. It's more, I would say, I want to clarify what the problem is, because the load is a little, we haven't seen a load like this before, so I'm going to try and cut through that noise. Okay. Does anybody have any questions on this? Okay. All right, if that's the case, let's pull up your homework assignment real quick. And do I need to leave this up? Okay. So this is the problem I've given you. And I know that the load looks a little strange. What?
Are you serious, man?
Just.
You're giving us the New River Gorge Bridge as a homework assignment?
That's next week. No.
You gotta sort the load, don't you?
Essentially, yeah. So. Let's all. Hold on. Okay. All right. So let's take a look at the problem, and maybe what I can do is help calm things a bit, because everybody's seeing this, and I'm already sensing the tension in the room. Okay. So first off, okay, the first thing I want to make sure that we're clear about is, is that this whole rounded part of the frame, that you can kind of ignore that. In other words, like, it doesn't matter that the frame has this, like, rounded part. You can just sort of treat this as, you know, here's a hinge, here's a pin support, here's a pin support, and there you go. Okay? Does that make sense? So you can ignore that. Okay. So how many reactions do we have? 1, 2, 3, 4, right? So what we'll do is we'll say 1, 2, 3, 4, right? So you all can figure that out. Okay. Now, the part that obviously looks a little strange is this load here. Okay? But it really isn't if you just break it down into its constitutive components. Okay, first off, don't forget we have this 100 kilonewton load right here. Like, we've got that, don't forget that. Okay, now if it's okay, what I'm going to do is I'm going to use different colors for up top to maybe try and explain the loads. Okay, so what I want you to do is think about this. Okay, so you start from 0, you go up to this, so this is 20, right? And then it's constant, and then you go from 20 to 40. Okay, does that make sense? So could I do this? Could I say, okay, let's have a single load that's distributed, okay, and then maybe 2 triangular loads. Come on. So have a triangular load right here, a triangular load right there, and then just a single distributed load. So this strange load is really just 2 triangular loads and a distributed load. It's no different, okay? So take the 2 triangular loads, you know, force and resultant, and do the same thing with this. So you'll have like a resultant here, a resultant here, a resultant here. Okay, does that make sense? Again, it's not any different.
You just missed it.
You won't get many likes on that one.
I think it'll be on roast.
I'll make comments.
Okay, yeah. Okay, does this make sense though? Does the problem seem a little bit more handleable? Hold on, wait, yes.
For the 40 kilonewton per meter, is that just the left side?
It's just the left side, yes. So think of it like this. Okay, so basically, like if you split this, this is 20, and this is 20. Think of it like a dimension, okay? So that means that this is 20, this whole magnitude is 20, and that magnitude is 20. So they're all 20. I don't view that as a structural analysis challenge, more as like just explaining dimensions. So that's okay. Does that sound good? Hold on, yes.
Like when we're calculating like the distance from A of the blue one, right? Or that green.
This is green right here. That's
That
green.
green. Like what about the feet on the left side? The extra 4 meters. Like, do we calculate that in?
Well, is the load there?
No, well, yeah.
Yeah, I mean, here's the thing. This is 20 kilonewtons per meter. This is what, 4 meters?
Yeah,
That's 80 kilonewtons, right?
yeah,
Gotta go somewhere.
true.
Yeah, so, I mean, the structure has to hold it up. So I'm saying that this distributed load is 20 kilonewtons per meter over a distance of 16 meters, right? 4, 10, 16. So it's all that, right? And so you're going to have a triangular load here that's 4 meters wide, a triangular load that's here that's 4 meters wide, right? So this is 16 meters, right? So you can figure out how far over that goes. So. Does that make sense?
Sure. Okay.
What's going on my Facebook?
See, every
Please
other
don't.
professor runs from the screen when you go to take a photo.
I don't care. All right, everybody good? Enjoy Monday off, everybody.
Well, I think my